Hello, welcome to NSSpain. My name is Vlad. I work for Avito, which is quite a large company in Russia. I'm part of iOS testing team. There are 4 of us plus 1 boss. We don't work only on test things. We work on builds, release pipelines, local developer experience, and CI. And today I'm going to talk about CI in depth. I will keep my agenda as simple as possible. I will cover CI and build farms. I will talk about our mistakes, our gotchas and catches, and other things that we learn during our way to better CI. When you're a single developer, indie developer, your CI is your Xcode. Xcode can open your project files, you can edit build settings there, you can also edit 3D scenes. Wow! But more importantly, Xcode sometimes can build your projects without Swift compiler crashing again and again. And Xcode sometimes highlight your source code files without SourceKit service crashing again and again. This is a simplified version of block diagram which shows your flow when you're a single developer. First, you write your code, then you build it and test, check for errors, fix them, commit and push. Build, test, commit, repeat. Build, test, commit, repeat. But when you're a part of a team, a lot of changes will be coming into your project. You'll have to make sure all these changes are reliable. So each check for each change may be called with a single word, build. You will have a lot of builds. Usually, you will run all these builds on your pull requests. For example, in Avito, we have all these builds running on every pull request. Each build, of course, takes some time. If you summarize all our build times, you'll get about 80 minutes for each PR check. But our developers wait only for about 30 minutes on every pull request for all builds to complete. In fact, 30 minutes is our P90 for all builds. How did we achieve 30 minutes instead of 80? That's a good question and very important one. To answer that, you'll need to have a continuous integration server first. There are plenty on market. For example, Jenkins, GitLab, TeamCity. Then you will need machines, the physical machines, to run your builds, and you'll have to write your scripts in which you will describe the logic you want to perform. In Avito, we use TeamCity as a continuous integration server. TeamCity encourages everybody to use it through TeamCity UI. So now I will provide you a canonical example of how we use TeamCity and how everybody else uses TeamCity. First of all, TeamCity has builds. Each build is just a list of steps that will be executed when you run this build. Each step is a simple invocation of some tool, or it can be an invocation of a script that you hard code right into the TeamCity UI. Somebody may say, oh, that's quite convenient, but you shouldn't do that actually. TeamCity encourages you to do that. It even has a bash syntax highlight feature built into the TeamCity UI, but you shouldn't do that, and later you'll understand why. Next thing I want to cover is build change feature. I don't think other continuous integration servers have something similar to this. Maybe yes, maybe not. But the idea behind this feature is simple. Instead of starting, for example, 10 builds on pull request, you start a single one. That single build pulls other builds automatically for you. For example, it can depend on run test. Then this build can depend on build test. So first test will be built, then they will be run, then the results will be reported back to pull request. That's very handy feature, allows you to parallelize your work across many physical machines. You can speed things up quite dramatically. Next thing, parameters. You can consider them as argument list to your build steps. Usually put there some passwords, usernames, secrets, but sometimes you can also put additional things. usually this list of parameters, unfortunately, becomes a huge mess. Everything I just described, we call TeamCity UI, at least in our team. There are some problems with it, though. The very first problem, and very important one, is that TeamCity UI state is actually detached from repository state. Let me show you a quick example and describe this issue in detail. Imagine you have a develop branch where you push your main everyday code. You can also have some release branches as well as usual. And then you want to add a new check to your code. You press Add Build Step button in the TeamCity UI. You fill in the script value with a new bash. For example, you want to check that newly introduced JSON file has the correct data in it after running some tests or whatever. And you verify that this check is green on develop. Everybody is happy. Then you realize your current version of the app in App Store is broken and you need to upload a hotfix release. What are you doing now? Of course, you create a pull request into your release branch and you realize that all builds are red. Why? That's because there is no such a thing as a newly introduced JSON file on that branch. That file exists on develop branch, not on release branch. Because TeamCity UI doesn't know anything about your repository state. It just runs scripts, runs your tests, runs your steps. Any ideas how to fix that? Of course, add some if statements to your TeamCity UI, right? No, I don't think it's a good idea. Another issue with TeamCity UI is that its state is detached from build machine state. Imagine we have a build machine with Xcode 11 and we use this parameter to run tests on iPhone SE simulator. If you update Xcode on that machine from version 11 to version 12, that build will crash because Xcode 12 doesn't know anything about iPhone SE now. It knows about iPhone SE first generation and second generation. Another issue with TeamCity UI, I call it imaginary flexibility in Bash. With all these UI niceties like Bash code highlighting, it's hard to avoid that. Usually you tend to add such things like build configuration, build destination, schema, workspace into your parameter list, and you read them from Bash and you invoke your Xcode build with these values. But do you really need to have all these parameters as parameters? Why not hard code them? Do you really want to change clean build to test in the middle of the road? If you need to start testing, create a new build. If you don't need to clean build something, delete the old one. Unfortunately, this doesn't work. It's kind of psychological thing, I guess. These parameters tend to appear in templates, and you base your builds on those templates, and later you can't delete those configuration parameters from templates because you don't really know which build is using what. All these parameters become garbage and kind of abandoned place in your CI. Nobody really wants to touch that anymore. Issue number 5. Any change in TeamCity UI is being tested in production environment. When you change parameter name from something to something and click Save, it's applied immediately for all future builds. And you can't be sure if it will break anything. And again, quick note about Bash, the lovely scripting language. You write it, and 4 days later you don't understand what's happening there. Like unique, sort, print, it's all messy. It's not very scalable. So writing CI in Bash, not really good idea. In order to solve the problems I've described earlier, we came up with ideas that helped us to scale and maintain CI easily. For example, now every TeamCity build contains only a single step that calls bash CI. Yes, bash CI, but that's very easy and small amount of bash that allows us to jump into Python and run our logic from there. Here is our typical example of our bash entry point that TeamCity build invokes inside its single build step. First, we import our bash CI. Yes, it's about 6-7 files. It's quite small though, and we don't change them very often. After that, we use exposed bash CI function to install Python with all dependencies, and then we invoke specific Python entry point for that particular build. This new organizational structure of our builds gives us plenty of benefits. For example, it reduces the number of bash lines of code to minimum. We can check for changes on CI right on pull request. We can write tests for our CI code. In Python, it's very easy to do, and it's ideal for monorepo. Although there are some downsides as well. It's not actually downsides. These are unavoidable downsides. If you need to add new check, you have to put if statements to support any historical build. Without them, those builds will break. We developed some good bash manners for ourselves as well. First of all, we introduced zero bash policy, which disallows us to write any new bash code. Second, and more importantly from developer perspective, is that we annotated all our bash code with this annotation set-xu-eo pipe file that enables bash debug mode. For example, it will print every statement bash is executing, which is handy when you debug on CI from build logs. It will crash fail-fast if you read any undefined variable. For example, if you refer any environment variable that is not set. And it will error as soon as possible if any exit code non-zero happens, which is also fail-fast approach to our bash. Python, turns out, is a very good language, but you advise to use technologies like Python version 3, PyEnv, Flake, MyPy. With all these tools, you will never make a typing mistake anymore. Having Python allows us to implement some extended logic to our CI. For example, if we change only markdown files, we don't have to run UI tests, right? So we can implement some impact analysis. Or if developer creates a new test or changes an existing test, we can run this test 5 times in a row to make sure it's stable enough and it's not flaky. We can also run additional checks. One good example would be if person changes a sign-in certificate, we can run release build to make sure it's not broken. Also, if any test fails on pull request, we can compare it to develop branch. And if it fails there as well, we can still let people merge their pull requests. Python reads things like username and password from TeamCity environment, but everything else we tend to keep in code. For example, paths to files, project names, scheme names, configurations names, and so forth, we keep in code. If we need to invoke any other tool, we generate arguments for that inside Python. How would you build your project, right? There are many approaches. For example, Fastlane, very popular technology written in Ruby. Of course, as every Ruby technology, it has its own terminology. Driving lane, fast file, all these things. The downside, though, is that vendor lock is huge. You implement the whole CI logic and even local developer experience in Fastlane. We didn't like that. Instead, we used Xcode. No Ruby, which is good, because we don't like Ruby in our team. Python wrapper. We created one for our needs, and we use Xcode build right from Python. We also enforce clean derived data in private location. In TeamCity, we force clean checkout, which removes that private derived data, and that means we are not affected by any history build that was running on this build agent. Another question is how to run your tests. There is a Xcode build thing. You can run tests on your local machine, even on multiple simulators, right? But if you need to scale across a build farm, across multiple Macs, there is no clean solution for that. We wrote MC, our in-house test runner that uses the whole build farm. Let me show you how MC works on our CI. Here's the list of our builds again. Let me concentrate on UI tests and end-to-end tests. UI tests took 14 minutes and end-to-end tests took 8 minutes. But if you get CPU time for those builds, it will be 6 hours and 22 minutes and 1 hour and 10 minutes correspondingly. Quite a huge time boost, right? MC is an open source project and is available on GitHub. Have a look if you're interested. Also, I presented a talk at NSSpain 2 years ago about our testing infrastructure in Avito. Have a look. Another question that comes is how would you code sign your projects, right? How would you code sign your applications? Of course, there are plenty of tools around that, I guess. Fastlane comes in my mind first, with its match cert and sci command. That's why we didn't use Fastlane, we used Xcode. But it has also automatic code signing feature built into it, and it didn't work for us at all, because sometimes it would code sign, sometimes it wouldn't code sign. You have to open Xcode, check the checkbox to make it work. That's not automatic if you have to check the checkbox, right? We developed our own in-house, how I call it, semi-automatic solution for code signing. How does it work? Quite simple. We commit certificate and mobile provisioning profile into repository. When we need to sign anything, we create a private keychain and add certificate into it. Then we patch Xcode project from Python and we set concrete team ID, concrete provisioning profile ID, and we set a path to private keychain as well as certificate name inside project settings. That's it. It just works after this. With our code signing procedure, it's very easy to update certificates as well. You just push and commit and create a new pull request. Bonus points, it gets validated right on pull requests. Even release builds will be run. When certificate expires, though, the whole iOS department will know about that, because everybody's pull request will be broken. It's good though, because if release build is getting broken because of outdated certificate, it's usually too late to know about that. You want to fix it, you are in rush. But when just you can update it normally without breaking your release build, it's much better for everybody. Where to build? You will need a build farm. This is how our build farm evolved over the years. In 2017, we had about 20 Mac Minis, but maintenance of them was really horrible experience. You had to use SSH, VNC, mouse clicking in GUI. Every Mac Mini had a different state. Updating macOS and Xcode was very difficult and tough experience for us. Over the years, the number kept growing. In 2019, we already had 55 Mac Minis, and we adopted Puppet. That relieved our experience a lot. Today we have 76 Mac Minis. Puppet is quite easy to understand software. What it does is it executes your rules every 30 minutes, and those rules tune the state of your machines up to the same level. Rules are simple to understand and they are idempotent, they have to be idempotent. Everything is good on this side. There are some bad sides as well. For example, Puppet uses different repository with bash code, usually bash code, because Puppet encourages you to write bash as well. Also, Puppet is written in Ruby, and that fact brings us some good interesting syntax like only if and unless. And combine that with bash failure exit code 1 instead of 0 and true false, which is 0 and 1, and your mind can easily break. For example, this is the statement unless test D folder, which means unless folder exists or not exists, like exit code 1, 0, true, false, unless, around that, in order to keep up with our zero bash policy and describe all the logic in Python instead of bash. We created Python for Puppet project. We do sparse checkout of our monorepo into private folder on build machines, but we remove everything else except bash CI and Python CI. Then we create new entry points for Puppet, just like we do for TeamCity builds. This allows us to express all the logic in Python instead of bash, and to commit changes into monorepo instead of private Puppet repository. We use CocoaPods as dependency management software for our projects. We install Ruby from Brew, and then install CocoaPods into that Ruby, not System1. This gives us ability to manipulate CocoaPods version without entering sudo. Also, we use bundler to control CocoaPods version through gem file. Using bundler allows us to update CocoaPods version through simple pull request mechanism. Here's an example how we update Fastlane. Yes, we still use it to upload our binaries to App Store. But we update CocoaPods using similar manner by just changing single line in a text file. We use Brew to install Ruby, of course. But couple of words about Homebrew. Here I'm trying to install Ruby version 2.7. What are the possible outcomes? Brew can install you version 2.7.0. Okay. Brew can install you version 2.7.1 because Homebrew has a auto-update feature and it decides to install that version. Okay. But also, Brew can refuse installing Ruby for you because open source community of Homebrew decided to remove the formula for Ruby version 2.7 entirely. They will think, oh, nobody else needs a Ruby 2.7 because there is a Ruby 2.8 already came out. We have to deal with that somehow because we need to have consistent state across all build machines in our build farm. To install all required formulas and binaries, we store them in private tab to be independent from global tab that is constantly changing. And tab means private Git repository, of course. Then we just tap it on our build machines from Puppet and install any dependency we need from our private tab instead of global tab. In this case, we just call brew install AvitoTab/speed/core utils. Now let's talk about build farms. As you know, having 36 Minix or Macs is okay, but having 75 of them is very bad experience in terms of maintenance. That's why we adopted Puppet. As an example, a single Mac Mini instantly dead after we purchased it. So far it's 1.3% of faults for us. Having too many computers in the system means we have higher possibility of some issues, like Macs not turning on or not booting. It means we have to have some alerts around. In order to have these alerts around, we developed a small daemon that we call machine metrics D. It can report back to our Grafana such things as load average, running simulators, swap used, number of running processes, free RAM, uptime. It starts when machine boots, and we can track these metrics as well as aliveness of each build machine. Another interesting aspect of having large build farms is electricity consumption. When we have 75 Macs and they are not under load, they consume about 700 watts. Under full load, though, they consume 3.6 kilowatts. The problem is UPS would shut down, in our case, the whole build farm if its consumption goes over 2.7 kilowatts. That was a thing for a huge investigation why at some point build farm would just shut down entirely. Outcome here is that you have to scale your electricity together with scaling your build farm. We benchmarked our build farm and compared it to some MacBook Pros we had around. For example, here you can see the duration of pod install. What outcomes can you do from here? First of all, our pod install takes 3 minutes, which is ridiculous amount of time actually. But also you can see that MacBook Pro is twice as slow as Mac Mini from 2018. Here we compare build time performance of our Avito app. As you can see, Mac Mini is still the fastest machine among others. Another performance chart. In this case, we compare the simulator boot time P90 value for 30 days window. You can see that Mac Mini from 2018 is twice as fast as Mac Mini from 2014. How can you squeeze even more from your build farm? Consider replacing your thermal compound in your Macs with a liquid metal. With that, you'll get 11% faster build times. Now, let's look back on CI problems that we discussed earlier and how we solved them. For example, having lots of bash in TeamCity, this bash has been replaced with bash CI, which is cleanly written 7 files, entry points in bash, which contains only 3 lines of code, and Python logic, which is clean, object-oriented, nice language. TeamCity didn't know anything about machine state. Of course, we tune and equalize all state across all build machines using Puppet now. Imaginary flexibility with some parameters have been replaced with CI encode, Python, and unit tests for our CI code. Garbage in TeamCity UI. Nothing we can do about it. We just keep cleaning it again and again. Testing in prod. We replaced it with a clean approach when we test our changes on pull request instead of applying them globally. My teammate, Artem Razinov, has came up with multiple CI values that are very important, and I'd love to share them with you now. Ideal build step consists of a single script call. Script should be stored in a monorepo with the rest of a code base. If you can store something in a code, let it be in the code. Less parameters and less environments is better. If something can break after merging a pull request, it must block that pull request. Pull request has single entry point for all possible checks, a single build. Every check is kicked off by that single entry point. Reuse build artifacts for various checks if possible to increase the build farm performance. That's it. Thank you for having me. Follow me on GitHub and Twitter. Check out our MC project. Goodbye.